Okay. So thank you, Yu Zheng, and now this meeting is being recorded. So today we will first discuss the solution to the lab, second lab. And afterwards, we will talk about the first assignment. I will just briefly discuss what do we need to do here. And yeah, but before that, I actually need to talk to you about something where we left off the last time. So I hope you guys can see this whiteboard, so to say. And you might remember that last time we were talking about probability, like just a review of probability, and there was a concept of expectation where we. Okay, so now we are good to go. So the last time we were discussing about a brief overview of the probability, and like at the time was up when we were discussing about expectation. So I just wanted to give you a brief uh, overview of like a brief summary of that before we move ahead. So if everything is still working, please give me a heads up because it seems that my video is again stopped. Okay, cool. So everything is working fine. Okay, cool. So usually, like when we talk about the random variables, we also talk about the expected, like the expected value of the random variable or the average value, so to say, that a random value is going to take. For example, let's say a variable is uniformly distributed. I don't know, between, let's say, between 1 and 2, right? And now if someone asks what is our expectation if we just talk about one value of this random variable, what value that could be? Okay, so in that case, let's say like it is like, let's say 1.1 and so on and to 2. So we will say that okay, this value like is maybe like sort of the middle value or something like that, right? Or in, just as I mentioned, in case of uniform distribution, we say okay, most probably, like of, we can just take an educated guess that this variable will be probably in the middle or something like that. So this is what we mean by expected value. And the mathematical way of writing this is like expectation of x, as we say it. Okay, so please remember that this expectation operator like can take different forms for different domains. Like for discrete domain, this is equal to like sum of x and uh, pmf of x, like for all the possible values that x can take. Similarly, if we are talking about the continuous domain, then we will say okay, this is equal to x and pdf of x dx, and the integral will be across the whole interval where x can appear. Okay, so this is how we define expectation. But like these are the mathematical formulas, and this is the notation in itself. The ease of using this notation is that it can be easily extended, and we need not use this like whole formulas. For instance, a simple intuitive way to extend this is, let's say we have any function. If we want to calculate the expectation of any function, this is equal to like uh, expectation over all the values that x can take and into pmf of x. And the same concept can of course also be extended in continuous domain just by extending this thing. The thing to notice is that the expectation is always with respect to all the random variables included inside. Okay, usually like it is better to explicitly type the variables here, and if we don't type the variables here, this means that this expectation will be with respect to all the variables involved. For instance, let's say if I have if I can say it, like if I say my expectation, like if I want to find the expectation of, let's say, I don't know, like anything, let's say x plus y plus 2xy. Suppose this, like this is a joint of, like let's say this is a variable z, which is composed of this composition, like this formulation of the random variables x and y. Okay, in that case, the expectation will be with respect to the whole joint. So we can say that this expectation is with respect to x and y. Usually we type it like that. So expectation with respect to x and y, and then we say okay, x plus y plus 2xy, and then we can again like keeping in mind that this will ultimately open up in some form like this, because this is a function of x and y. So we can say that this is equal to expectation of x y x plus expectation with respect to x y of y plus expectation of 2xy with respect to xy. And since in this term we don't have any presence of y here, we can drop this and we can say okay, this is expectation with respect to x, plus here we can say this is expectation with respect to y, plus here we have both. And since this 2, we can also take 2 out of this brackets, and we can say now in like this term, in the third term we have this formulation. Okay, so you see we were able to break this function down. And actually the thing is, when you start doing like when you start doing this thing, when you start going from this step, like from this step to this step, in the beginning of course you can only be able to do that if you have these formulas in your mind, okay, these two formulas in your mind. But once you get a practice, once you get a feel of that, after some time you sort of stop thinking about, sometimes like you stop explicitly thinking about the formulas, and you start working in terms of these expectations, and only when it is required you can then open the formulas in your mind. So this is how it works. If you guys have any question till here, we can take it, otherwise we can proceed. If there are no questions, maybe you guys can um, sort of give a yes or no or something like that, so that I know we are still together and we can proceed. Okay. Yeah. So I get some yes and some no. So okay, if you guys have any question, maybe you guys can also type in the chat so that I also know that okay, we are sort of on the same page. So that was all about the expectation that I wanted to discuss. In fact, there is sort of an auxiliary concept that I also wanted to talk about, and that was law of large numbers. This is the last thing that we discussed last time we met. And so the law of large numbers is sort of a way to tie up this expectation, this expected value, with the with the empirically observed values of a variable. Okay, so for instance, if we have, let's say, I mean, let's say suppose we have a weird coin, some sort of a bent coin, so to say, where there is high chance of getting a head and low chance of getting a tail. So let's say like there is 70% likelihood that we will get a head, and 30% likelihood that we will get a tail. So this is the PMF of that variable. And if you ask, and usually what we do is, let's say we change head by 1 and we change, like we denote tail by 0, let's say. And when we find the expectation of this variable, this will this will be of course 0.7, because like 0 into 0.3 plus 1 into 0.7, and this will be equal to 0.7, right? Now this is how did I do that? I actually solved the same formula in my mind. So that was like expectation of x, that was equal to x px, that was like, there is when the value of variable is 1, we have 0.7 chance of that, and for value of 0 we have 0.3 chance of that. So this is equal to 0.7, right? Now this is the expected value of the variable. But suppose if we didn't have this probability distribution, or like let's say if we had this distribution but we didn't know the values explicitly, we only we only had the samples of this distribution. Okay, in that case what we can do is, let's say we have 1,000 samples, we can see okay, how many samples are heads and how many samples are tails, and we can sort of take the relative frequency of that. And this relative frequency also reaches also approximates this PMF that we have mentioned here. So this is the law of large numbers, that if the samples are large enough, the expected value of a variable, which we compute using this PMF, or like using the probability distribution, this expected value ap- is approximately equal to the average value of the samples of the samples that are drawn from that distribution. Okay, so this is where we stopped the last time. So if you guys have some questions still here, you guys can ask me. Otherwise, we can proceed. Okay. So if everything is okay, maybe you guys can say yes, so that I know and we can proceed. Okay. I see one yes and okay, and one in the chat. Okay. I guess that's so. If you guys have any questions, please let me know. So this was what I wanted to discuss about the. Can you make an example for large numbers, please? Okay, so like there is a sort of a suggestion from Yuan that can we make an example of large law of large numbers? So for that, actually, this law of large numbers is very useful in the cases when we practically are approximating some function. Usually, usually it is very useful in approximating something like that. For instance, suppose we don't have a like suppose we have an expectation of something like of a function xy, right? And this function can be a very complex function, suppose right now we are dealing in the continuous domain. Okay, and so that will require an integral over this like in fact like sort of like the integral like that, and we will have f x y and p of x y d of x d of y, and this integral, many times this integral is intractable. Okay, this is not, it's not very easy to find a closed form solution of this integral, right? So in that case, we usually fall back to this empirical methods, which is governed by a law of large numbers. So, for instance, right, we say, okay, we don't uh, we don't need to exactly compute this integral, but what we do is we draw, let's say, we draw 10,000 samples from this distribution. Okay, so we have this p of x y at hand. So what we do is, let's say we have, I don't know, 10,000 samples, like x and y samples from p of x and y, right? We draw 10,000 samples from, suppose this is a joint Gaussian. So we draw 10,000 samples from that joint Gaussian distribution. After that, what we do is we simply make, we simply calculate the function values for those samples. Okay, so like we had, let's say we have xi and yi, these are the samples. Okay, and these are like these 10,000 samples. For every sample, we calculate this function, and in the end we divide it by 10,000. Okay, and this will be nearly equal to, I mean, in simple cases, I would say. Of course, we will probably need a lot of samples for complex cases, but for simple cases, this will be nearly equal to this expected expectation of this function with respect to x and y. So you see, like if we had this intractable uh, integral, we sort of made our way around that by using samples instead of computing the exact integrals. Okay, so this is a way of breaking down the complexity, because often we are not interested in the exact computed values, but we are mostly interested in the approximation many a times. So this is one of the cases where this law of large numbers comes really handy. So now, okay, great. So now we move on to the next part, and there was actually a small. Let me see. Yeah. So there was actually a small proof that someone has unmuted themselves. I would request you guys to please keep yourselves muted so that all the students can hear. Okay, thank you. So now we move to after that I just wanted to go together with you guys through this proof. I mean, this is a really simple proof, but this again sort of is a small exercise which will help you also to do a task in the assignments, and in general also to develop like how we solve these approximations, um, and like how to derive things related to this like axioms or like proofs, so to say. So here the statement is that if x is like if x is p-dimensional real random vector, and XIRIID. We have discussed that already, right? So identical and independently, like independent and identically distributed, and such that for any component of X, uh, of course, so for any component of X, the probability that X square is less than beta is less than one for some beta. So we are, suppose we are given any beta, and we know that for this like the probability that X square is less than beta, this is less than one for any beta. And what we want to see is that as the dimensions of this variable keep on increasing, the samples tend to lie in the tail, so the samples tend to become far from center. So this for any beta, the x square becomes greater than beta. Okay, so this is what, like, it doesn't, the samples tend to lie not towards the sample center, but towards the tail. Okay, so if you see, like, the proof is really simple. I just wanted to go through that with you guys so that you guys just understand how it's working out. So this is what we want to see, that what is the value of this thing, right? And this is equal to, we know that this is equal to summation over all the components xi square, right? So probability that the norm of square norm of square Euclidean norm is greater than or equal to some real number beta. This is I have just like sort of opened up this norm, and this is exactly equal to this probability. Okay, now you see these all values are greater than or equal to zero because they are all squared. Okay, so it is like saying x1 square plus x2 square, let's say, plus x3 square is greater than or equal to beta, right? So you see, there is more chance that this whole thing is greater than beta compared to one thing, because these are all adding something to this term, right? These are all adding some positive, some non-negative value on the left side. So if we only pick, let's say, one term from these three terms, there is less chance that it will be greater than beta. Okay, so that's why we say that this probability, this thing, is greater than the probability that xi square is greater than or equal to beta for one, like there is like different way of mentioning that, but as it is mentioned in the notes, for at least one I. So in other words, there should exist at least one I so that xi square is greater than beta. Of as we can see here, that there is more chance that this whole summation is greater than beta compared to taking only one term. So you see, if you are saying that at least one should be greater than beta, there is a concept of complementary events. Like in the probability case, for example, if we are talking about this, that the probability this probability is 0.7, this thing, then the probability of the complementary event is the event that is totally opposite to the event that is currently taking place. So a complementary event is the event that, like, two events, if they sum up to one and and they are exclusive together, we say that these are the complementary events. So like, for example, head and tail, tossing of a coin, coming up of head or coming up of tail, they are complementary events. So the probability of head is equal to 1 minus probability of tail, right? Similarly here, the probability that at least one is greater for at least one I xi square is greater than beta, the, we can use the complementary event, which is xi square is less than beta for all I, right? So this event is totally complementary to this event because they both sum up to 1. Now for all this thing, for all I can be written as like I is equal to 1 to p, and probability that xi square is less than beta, right? Because they are IID, that's why we were able to break down in independent distributions. And as a result, we have probability that xi square is less than beta. And here we have this uh, power p, right? Because we had p times this the same probability. And this approach is 1 because this is less than or equal to 1. So the as p approaches infinity, this thing approaches 0, right? This term, as a result, this whole term approaches 1. So there is this concept of complementarity. This thing that we did here, this is also something that you will probably need when doing the assignments. Why can we write it as a product? Okay, yeah. So I guess this is a question from Patrick. I guess related to this step, that why we were able to write this as a product. So it's like saying, let's say we have three variables x, y, and z. So if I say probability that x is equal to 1, y is equal to, I don't know, let's say I don't know, let's say 2, z is equal to 3, right? So this is we have seen that we have seen last time that this is equal to probability that x is equal to 1, and probability that y is equal to 2 given x is equal to 1, then probability that z is equal to 3 given x is equal to 1 and y is equal to 2, right? You might remember we opened up joints in terms of marginals and conditionals. So and then after that we saw that if because of this independence, because of this IID conditions, we know that probability of 2, like we know that this will be equal to probability of y2. Like if x okay, let me write here is equal to, and here let's write x, y, z are independent. In that case, it will be equal to probability x is equal to 1, probability y is equal to 2, probability of z is equal to 3. Okay. So because we know that getting a knowledge about value of x will not change our probability distribution of y. So that's why these two things are equal, and similarly these two things are equal if this condition holds, if this is the knowledge we have, so to say. So this was the reason why we were able to neglect these conditional parts. And the second thing is, since they were IID, like the probabilities were independent, that's why all these values took the same like this was equal to, let's say, q for all I. Like no matter if we are talking about I is equal to 1, I is equal to 2, I is equal to 3, whatever, this will take the same value because the probability distributions are identical. Okay. Like for example, if let's like we have all the coins are bent, let's say, right? So, where was that example of bent coins? Yeah, like here. Suppose we have 1,000 coins and all the coins are equally bent and all the coins have same distributions. So we toss all these coins, like all the coins one by one, and the answers will be. I mean, these coins will not depend upon each other, and the probabilities will also be identical. That's why we're able to do that. Okay. So these are the two things that I wanted to talk to you, and now I guess we can take a small break and then we will continue with the solution to the lab, and then in the end we will just briefly discuss what assignment we have to do. So let's take a break till like for 4 or 5 minutes, let's say. Recording. Okay, cool. So if you guys can see the screen and hear me, just give me a heads up so that we can proceed. Okay, cool. So the lab was related to statistical decision making, and let's arrange that side by side. So the first task was related to this joint PDF of two variables, and in fact we have also done like we also did a similar example the last time. So consider a two-dimensional discrete random variable x, which consists of two random variables x1 and x2, subjected to a joint distribution px as described in the following table. The first task is to compute the marginal probability densities px1, px2, and the conditional probability of x2 is equal to 0 given x1 is equal to 0, as well as the expected value ex and covariance matrix. So yeah, in the first task we need to compute quite a lot of things. So let's start. So the first thing is okay, before we jump, I just want to. I mean, there are. I mean, this is a simple example, and there are a lot of ways of solving that. I just want to briefly mention the way we will proceed with that. So, if you guys can see the screen here, so this if you guys can see the x vector consists of two variables x1 and x2, and we will describe these two vectors in this form, like in a real vector of 2 cross 4, right? So like the first column is 0 0, means the first like value that this joint variable can take, then 1 0 0 1 and 1 1. Would you please make it bigger? Okay, I hope it is better now. So this is how we will be defining our variable, and similarly the probability will also be defined in a similar way. So like we will define the probability as probability 0 0, probability 1 0, probability 0 1, and probability 1 1. So so that we have like we have a coherence here, like this 0 0 refers to this refers here, and so on and so forth. Okay, so this is how I mean we will sort of architect our solution. There are a lot of ways to do that, and because this is a simple example, you can proceed with in whatever way you like. Now that this is clear, so the way to do that is we start. And, I mean, this is just an example that I have given to you. You might remember that we mentioned here that one of the functions that you might need is this rebel function. This returns a flattened array, and there are different ways of flattening an array. We can use, like, suppose if we have declared a variable range from 1 to 10 and reshape it in 3 by 3. Okay, let's see how does that appear. So this is the range from 1 to 10, and we have reshaped that in a 3 by 3 matrix. Now if we flatten that, if we simply call this rebel, what it does is it flattens row wise, so to say. So first it goes through the first row, and then second row, and then third row. If we use this 410 style, there are different styles. You can in fact go through the documentation. There is a column measure, row measure, and 410 style, things like that. So if we use this 410 style, it sort of goes column wise, like first 147 258 369. So these are column wise, and then of course we can do all the things with that. For example, doing that will only sort of give the divisor, so to say. Like this array is divided, we simply are dividing this array by 2, and we only are getting the quotient, so to say. So like for example, we know that 7 divided by 2 is 3.5, but we are only interested in 3, so the integer value, so to say. So now that we have seen this small detail, let's move ahead. So we define the probability table as given here. So this, we define the same probability table here, and uh, and then we define uh, the instances, the possible values that our vector can take, right? And then the marginal distribution, the first thing is to compute the marginal probabilities, and we know this is really simple. So for example, computing right now we want to compute the marginal px1. So px1 is simply computed by summing up across x2 axis. So x2 is right now the column axis, so we sum across all the columns and we get px1. Here you can see we sum across axis 1 and we get px1. Similarly, we sum across the rows axis 0 and we get px2. That's as simple as that. So here we have printed out the marginal probabilities, and you can see like this 0. 0.7 and 0.3. Like if you sum these two, 0.4 and 0.3 is 0.7, and similarly sum of these two is 0.3. That's all is what's happening here. Then for conditional probability, um, so we wanted to find the probability of x2 is equal to 0 given x1 is equal to 0. So this is the probability we want to find, condition that we know this. So for that, we know we first want to we first want to marginalize this first row by the sum. So 0.4 plus 0.3 equals 0.7. So we marginalize it by by the sum, and and then and in fact that's all there is to it. And then we pick up the first element. So that's what's happening here. If you see marginal probability, sorry, this p of x2 given x1, right? Because this p of x1, this is already we have already computed the marginal probability, so we simply use that computation from here and divide this first table cell by this value. And then we want to find out the expected value. So the expected value, we have already seen the formula that for expected value we need to multiply every value of x with the probability of that value. So for example, one value of x vector is, like, let's say 0 0, another value is 1 0, another value is 0 1, another value 1 1. So for every value, we will multiply that with the respective probability. So that's what's happening here. So what we do is we flatten this matrix. As a result, we get this type of flattened vector, right? And this, this first value, this 0 0 corresponds to 0 0.4, 1 0 corresponds to 0.3, and 0 1 1 0 corresponds to 0.2, 0 1 corresponds to 0.3, and so on. So after that, what simply needs to be done is to simply multiply this together. If you remember the formula, we multiply every value with its probability, and that's what's happening here, right? So we take a multiplication of x with the flattened form of the probability table. That's all it's happening here, and it gives us the expected value. And here is the expected values. And after that, we need to find out the covariance matrix, and we have also given the formula for covariance matrix. So expected value of x minus mu of x, like mean of x, so to say, the expected value of x, and the same value but in transposed form. So here, before reading that again, I will go back to this whiteboard, and you can the way we implement that is, if you see here, the formula for covariance is given by x, like this is the same vector that we multiply with its transpose, right? So we first calculate this vector, like x minus mu of x, and we say this is equal to x of c, like centered x, so to say, like centered around the mean. And after that, we simply need to find this transpose, and we will and then take expectation, and that will be all. So if you see here, this will actually be a matrix, right? And the matrix will be of the form, as we can see here, like this is the first element, and then we have the second element here, like xc transpose, but the second element only here. And similarly here we have one, like the 1 0 element of xc and xc transpose, and here we have 1 1 of xc and xc transpose, right? So this is what we want to achieve, this is what we want to get. Okay, and a simple way of achieving that is that we already have this vector x, we can simply transpose this vector, and in the middle we can create a diagonal matrix where the diagonal is filled with the probability values, right? And what will happen is, if you see, if you solve this matrix, if you solve this multiplication, you will see, for example, for instance, let's solve this let's solve these uh, first two matrices. So it will give us uh, this matrix as I have already mentioned here. So x0 into p1, x1 into p2, and all that. And then once we solve this further, this is sort of the first uh, these are the elements that we will get in the end, and this is like the first element that we will get. And when we multiply that with the values, so we will get zeros and ones, and in the end we will be left with exactly the same form of the matrix as here. So in the end, what I want to say is, if we compute this matrix, this computation will give us exactly this covariance matrix. So that's what we are doing here. So we first find this x center, and of course we have found the mean. So what we do is, we find x centered by using x minus x mean. Now another thing that you should also know is, like x is, for instance, right now like that, right? We have two rows and four columns, and x mean, of course, has it has this form, like it has two values. So what we want to do is, we want to make four copies uh, of the same value. So the way, yeah, I know, okay, I guess the notes are not that important right now, that's why I did that. Anyways, okay, sorry, you're right. So uh, the way to do, the way to do is to, of course, broadcast, right? So what like for example, this x has, let's say this x has n values and d dimensions, right? But the mean of x will only have one, it will only be 1 cross d, right? So we need to broadcast, we need to add an axis here, like I have mentioned here, so that numpy understands that, okay, we want to subtract this mean from every value of x, right? That's what's happening here. We can use these expand dimensions, we can use new axes, or we can use the notation, you might remember, uh, we used this notation in the last tutorial. So this is already also commented here. We expand the dimensions because we um, want NumPy to understand that, okay, we need to broadcast this. So we need to subtract this vector from the whole matrix column by column. So that's what's happening here. And once we have this centered x, we can simply, after that, we simply do this computation as we have already seen, this one, right? So you can see here, what we are doing is, x centered multiply by this multiply by a matrix which whose diagonal entries contain this flattened probabilities table. And once this multiplication is done, we have an outer multiplication that involves transpose of the same x center, and this is a covariance matrix, as we can see here. So you can see that right now we have done all that using the probability table and the actual values of x. We have not used samples at all. But now we will also, when we go forward, we will also use this law of large numbers as we discussed, and find out uh, how it corresponds to the expected values. The second task was to make a Python function toy_rand that expects a positive integer n and outputs and returns a matrix x of size 2 and n containing n samples drawn from probability distribution px as its output. So you see, now what we want to do is, now we want to write a function that gives n samples from the same distribution, from this probability distribution, right? This is our next target. Now once we generate the samples, after that we will see the sample means and sample variances, and we will see how close they are to these values. Okay, this is how we will proceed. So right now this function takes n, which is the number of samples it should output. So here again, before going into the function, just let me state what's happening here. So what we are doing here is, we know that x can take like this x vector has like two, of course, two binary vectors, x1 and x2, and they can take like 0 0 0 1 1 0 1 1, right, these values. And the next thing is, why not uh, like sort of join these vectors in the form, like join these variables to form an integer, so to say. So this is like 0, this is 1, this is 2, and this is 3, right? This is just binary encoding. So we can say that x takes these four values, right? And after that, now we want to see the probability with which x takes 0, 1, 2, and 3, right? And let's have a look at the probability distributions. So we can see that this value is taken with the probability of 0 0.4, and then we have x1 and x2. This value is taken, x1 is 0, when x1 is 0, we have 0 0.3, here we have 0 0.2, and here we have 0 0.1, right? So we want to generate x with this probability, right? We want to generate n samples according to this probability distribution. For instance, if we generate 1000 samples of x, about 400 of them should be 0, about 300 should be 1, about 200 should be 2, about 3 yeah, about 300 about 200 should be 2, and about 100 should be 3. Okay, so this is the concept that's working here. So that's why what we do is, first we define the value that we will output in the end. So this is just, we simply define a zero matrix of size 2 and n, and this is where we will populate the actual values. So we define an array of a zero array of size n, and we get uniform samples of of size n. Okay, now what we do is, we say, okay, since this is a uniform distribution, we say the values, we say the points where you know this distribution is between 0 and 1, just to let you know. So we say, okay, the values in this vector where this vector is greater than 0 0.4, we give them the value equal to 1. So what will happen is, if you see, if let's say if this vector was, let's say if this n was 1000, so we will have about 600 values where t will, because this t is distributed uniformly between 0 and 1. So if we want to see the values where t is greater than 0 0.4, this will be how much? 60% of the vector. So 60% of the vector will be around 600 values out of 1000, right? So this is what's happening here. So we say, okay, the first cut is made at 0 0.4, okay, because this q is by default 0. Okay, so just to show you in another way, this q is by default, this q is by default 0, right? And suppose and now we have another t vector, random vector, where values are between 0 and 1. So we say, if the values are between greater than 0 0.4, we give the value equal to 1. This means that approximately 400 out of 1000 values will be left here, and all these values will become 1. And the next cut is placed at 0 0.7. Then, so this was like 0 0.4, then we say at 0 0.7, so the values that are greater than 0 0.7, we say that here, okay, let's mention here, this is equal to 1, and this will be like around 300 values, so this will be equal to 2. and the next cut is placed around 0.9, so around here. And here we are looking, this will be, so because we have placed a cut at 0.9, so we are here talking out of 1000, just as an example. So here we will have values around 100, and they will get the value equal to 3, as you can see here, right? So what happened here is, you can see this part of approximately this part remained at 0, approximately this part remained at 1, approximately this part remained at 2, and this part remained at 3. So now you can see this part is around 0.4, and this part, which is between 0.4 and 0.7, this part is 0.3, this part which is between 0.7 and 0.9, this is 0.2, and in the end we are left with 0.1. So this is exactly the probability distribution that we have here. So 0.4, 0.3, 0.2, 0.1. So it is like dealing with like making making a samples sort of in a CDF type of way. So we are sort of accumulating the probabilities. So 0.4 plus 3 is equal to 0.7, 0.7 plus 3 plus 2, 0.2 is equal to 0.9, and this is all we need. So, and by default it was 0. So as you can see here, so about 40% is 0, about and then about 30%, which is the difference between these two, is 1, and then about 20%, which is a difference between these two, is 2, and about 10%, which is the difference between 0.9 and 1, of course, will get the value 3. So now we have a now we have this vector q, which has the values 0, 1, 2, 3, and these values are in the similar ratio as we have defined in the probability in the joint probability table here. So now once we have this, now what we simply do is we take the quotient and take the remainder. So the quotient is assigned to x0 and remainder is assigned to x1. And then we recover this binary representation of this variable. Okay. So let's say if this value was 3, so this means x1 is equal to 1 and x2 is equal to also 1. So this is what we recover in the end. So now we have formulated this function. I mean, this you might think this might be a bit complicated way of defining this function. You guys can define it the way it suits you. Like, there are a lot of ways of doing that, and this is just one of the way. So once we have this function at hand, the next thing is we want to find the empirical values, and we want to match them with these expected values that we computed in the part A. So the way to do is, of course, and they said like we want 10,000 samples. So from 10,000 samples, we get 10,000 as like we will get 10,000 samples, and after that we find the empirical probabilities, right? And this is quite x is equal to x1 is equal to 0. These are the marginal probabilities, so to say. So x1 is equal to 0 and x1 is equal to 1. These are the marginal probabilities, and they are defined simply by summing up the values where x1 is 0 and 1 and dividing them by total number of samples. And same for x2. So this is how we define, like we can get the marginal probabilities. So like getting all the samples and dividing them by the number of uh, total samples. Once we have marginal probabilities, we can use the same. Here we are simply concatenating them, so to say, like joining them to form the margin, like to form a single numpy array. And now we can see that this value is 0.7008 and 0.2992, and you can see this value is quite close to where is that, yeah, 0.7 and 0.3, right? So this sample probability is quite close to the actual probability distribution. So this is what happens. And just to show you guys, if we take n equals 100, okay, no, this was a magic number maybe. So let's say if we take n equals 1000, you can see now the probabilities are 0.72 and 0.28. They are like a bit different, not that much, but a bit different from the expected probabilities, which are 0.7 and 0.3. And if we the when we keep on increasing the samples, the probabilities also get refined and get closer and closer to the uh, to the real probabilities. So let's say for this many samples, you can see now it is like 0.69954. So it is really close to 0.7. Similarly, this is also really close to 0.3. So we will return to 1000 samples, 10,000 samples. So now that we are done with that, the next thing is to find the conditional probability where x. So we want to find out the probability where x two is equal. We want to find the conditional probability of x2 condition on x1 is equal to 0, right? So for that, again, this is again the same thing that we did uh, for marginal, and we can use the same concept. We can use the number of times that this value occurred where x2 and x1 were both 0, and then we divide them by the value where in order to normalize the probabilities. And this again, this is 0.569, and the value actually that we obtained was 0.571. So they are also quite close. So this is actually the law of large numbers that is working here. So we only based upon the samples, we were able to find out approximations to the probabilities and conditional probabilities, and also means and variances, as we will see afterwards. So the empirical mean, this one is quite simple. We simply sum up all the values and divide it by total samples. And for empirical variances, we have a formula already given in the assignments. So we will use the biased estimator. I mean, I guess we don't need to go here in depth, but the unbiased estimator has n minus one, but we need to worry about that. So this is the formula for empirical covariance. So if you see, exactly similar thing is happening here also. So this thing in the bracket, if you see, this is just the mean, right? This is just the empirical mean. And after that, what we are doing again is, here usually we had expectation, and now we have x minus mu, like mean of x, and x minus mean of x transpose. So this is quite similar to this thing, but this expectation is changed with summation. So with summation here, in the outward expectation, also in the inward expectation here. So this is just like the same formula in part A, but expectation has been replaced with the summation. And the way to do that in matrix form is, again, we expand the dimensions to form to find. We already have empirical mean calculated. We expand the dimensions so that it is subtracted from the whole x. And once we have that, we simply need to take transpose of these two vectors. So x observed minus empirical mean into x observed minus empirical mean transpose, and then uh, this matrix already takes summation, and we divide it by the number of samples to get empirical variance. And these values are also quite similar to the values that we obtained here. For instance, like here we have 0.21, and here we have 0.209. So quite close, I would say. So this was task one, and I guess we need to hurry up a bit. So the task two was related to MNIST. MNIST is a training set consisting of 0 to 9 digits 0 to 9 stored in PNG files of 28 by 28 pixels, and we have also the zip file which you need to download in the folder where you have this Python notebook, a Jupyter notebook. And these values are in unsigned integer forms, unsigned integer 8. Why? Because the values are, the maximum value is 255. So, and in 8 bits we are able to represent that. That's all. So what we want to do here is, we want to load two arbitrary images from like I1 and I2 and normalize them. That is like divide them by 255 so that the values lie in the interval 0 and 1, and just, I would say, just display them. So we define the folder, and we just take two images. And you please have a look. This is the format of the folder. So D2 means digit number 2, D3 means digit number 3. So like all the digits which have the value 2 are in this folder, D2 and D3. So they are like from D0 to D9. And then after that we have like let's say this is seven number digit number 75. Of course the digit is 2, but this is the 75th file that is present. And similarly here digit number 13, and there might be like 1000 digits in D3. They will all be 3, but they will be indexed like that. So we load these two digits. We use image IO. I mean, you can read about that if you want to. This is a simple image manipulation package. So we read from path 1 and read from path 2, and we change the type to float 64 as asked here, and we normalize them as so that the values are in 0 and 1. And then we just to show you guys, I have just plotted one image here. The next thing is to take Frobenius norm. So there are three different ways in which we are asked to take the Frobenius norm. So Frobenius norm is matrix equivalent of Euclidean norm, and it is defined as the trace of A transpose A, and then finally the under root of that. So if we have two matrices, the Frobenius sort of we can take the calculate the distance by taking Frobenius norm of I1 minus I2, as we can see here. So we will do this in three ways, and we will see that all three ways work. So one way is numpy.linearalgebra.norm with for Frobenius parameter. Another way is to directly apply this equation. The third way is to only use Euclidean distances between the vectorized images, because we are only interested in traces. So if we only calculate the distances between vectorized images, we will only be targeting the diagonal, the trace of this matrix, and this is all we need. We don't need to calculate the whole matrix if we can calculate the trace in some intelligent way. So first way is using this NumPy linear algebra. The second way is, as I mentioned, we use A transpose and A. Here we use matrix multiplication, and I1 and I2, I1 and I2 transpose. So because here we are like this is because of the difference between rows and column vectors. That's why we first use the simple one and then use the transform, and then use the transpose, and then we find the trace, and then we find the square root, just as in this equation. And the third way is to simplify, like to simply flatten the matrix to vector form, and then take Euclidean distances. This, and you can see all these values are the same. If you guys are with me till now, maybe you can give me thumbs up or something like that. If you guys have some questions till now, you can ask me. Otherwise, we can proceed. Okay, I saw a yes briefly and then it disappeared. I hope you guys can hear me, right? Okay, cool. So the last, I guess this is the last task, right? Yeah. So the last task is um, we want to train a k nearest neighbors classifier, right? So the way we want to do that is we want to have 500 images as training images and 20 and 10 images as test images, and we want for every test image to be classified based upon 20 nearest neighbors. This is what it says in like here in the detail. So we want to first load, like we want first we first load two different images, for instance 0 and 1, and we load 500 images of both the classes. Okay, so in total we load 1000 images. After that, after this 784 means the pixels were 28 by 28. That's why the training size is, and 28 by 28 equals 784. So that's why the pixels the training size will be 784 by 2 into n train, because we will be dealing with two classes right now. So it will be like 784 by 1000, because n train is 500. And so you can already see that we will be dealing with the images in vectorized form. So we will sort of make a vector out of the images. And so the way we will proceed is we choose, let's say we choose that first digit is 1 and second digit is 7. So we want to make train a kernel classifier between these two images. Okay, and then we just simply make like join them in one array, and after that we make the placeholder variables where we will keep all the values for this train and test images. Just a moment guys, let's have a 2 minutes break. So guys, sorry for this delay, and now we're back. So the way we want to proceed here is we have the placeholders, and now we will populate them with test and train variables. So what this loop is doing is it is populating both types of digits like ID1 and ID2. Okay, and it is doing that in parallel. That's why, so we go from 0 to n train. Like n train is right now 500 as we see. So we have a range from 0 to 500, and what we do is the first part uh, till till 500 will be populated in this line, and the second part from high 500 to 1000 will be populated in this line, right? That's why we have here 0 into n train, here we have 1 into n train. So this will be from 0 to 500. This line will populate this x train variable from 0 to 500 index, and this line will populate it from 500 to 1000 index. Okay, so this is how we will like this is the format of the image path for the digit 1, and this is for the digit 2. They are exactly the same. The only difference here is we are using d0 and d1. Okay, like d0 is this, d1 is this, and this is just to use the format as we saw here. So we want to access the images because the images are like the file formats are something like that. So for instance, here if we had 1, then we want to have d1 slash d, and here again is 1 underscore, and here these values will go from 0, like from 1 to 500, and zfill will make sure that the values are in this format, like zeros, that we have padded n of these. So that's all. So this is just defining the file path for different indexes of digit 1, and this is for digit 2. So digit ID1, digit ID2. Digit ID1 is 1, digit ID2 is 7. We can choose whatever from between 0 and 9. And what this variable is doing is we are declaring two numpy arrays. One is the numpy array of zeros of size 500. One is the numpy array of 1 of size 500. So this means The first 500 values will be 0, the next 500 will be 1. This is like the labels, the output values that um, we assign to different digits. So it is a way of for us to understand that, okay, if the value is 0, this means that we have digit id 0, digit id 1, like that was this one. If the value is 1, that means we have the second digit, that was this one. That's all it's doing here. Exactly the same thing is copied for the test data. Okay, exactly the same thing. The only thing different here is this end test. Here we had end train, here we had end test. Now we populate the test variables, and similarly we define y test also. Now we have x test, y test, x train, y train. The way you guys already know, the way k nearest neighbors works is it checks the distance of every test of point with all the training points, and then it sees the nearest points, nearest k points around every test points, and then it takes a majority vote, so to say. Like, let's say if 6 out of 10 nearest neighbors say, okay, this should be, we are in class number 1, so the test point will also go to class number 1, and vice versa. Okay, so for that we first define a distance matrix. Okay, and it will be of size 2 into n test, 2 into n train, because we are dealing with the two digits. So here what we are doing here is we are calculating for every test digit, we are calculating its distance from all the training digits. Okay, the way we do it is we have here x x test. This is like a single x test that is at ith index, and we again broadcast it. We expand the dimensions so that the difference can be taken from the whole x train vector, like all the 500, all the 1000 vectors, so to say. And then we take its square, Euclidean, and distance, and in the end we take like summation, and we do square root. This is exactly the formula that we already saw for computing the norm. Once we have this whole matrix, after that we check this matrix. We sort this, we get the arguments for sorting this matrix. Okay, so arg sort will give us back the indices as required for sorting, as it already says here. So x is equal to 1 means we want to do this along this axis, right? Because this is the axis that is being populated by the training samples. So what happens here is every for every test for every test point, we run this arc sort for all the training points to find out which training points are closest to this particular test point. So the point that is closest will come in the first place, because of this, the index of the point that is closest will come as the first one, and the index of the second closest point will be the will be returned as the second index, and so on. So once we have these indices, we can simply take a cut at k, because this is k nearest neighbors. So we are only interested in the k closest neighbors. So for every test point, by cutting that, by using a cut at k, now we have indices of the k nearest neighbors for every point. This means for like this is means that this operation will be done for all the test points, right? So for every test point, we will cut this array at index k, right? So as a result, we will have the top k index, the closest k neighbors for every test point. So this is exactly what we needed to decide in which class the point will fall. Now we remember that one class was represented by zeros and other was represented by one. Okay, so a simple way to find out where a class should fall is, we what we do is we simply take the summation of the training, like what we are doing is we are taking summation of these zeros and ones in y train. Okay, and the indices will be, of course, the indices of nearest neighbors, and then we will divide it by 20. So what's happening here is, let's say we had this value gives us 20 points, and some of those are zeros and some of those are ones. So when we divide it by k, we will get a value between 0 and 1. If this value is greater than 0.5, this means that more than half of the points here in more than half of the nearest neighbors were giving a value 1. Of course, only then we can get a value greater than 0.5. Similarly, if a value is less than 5, this means more than half of y train nearest neighbors were giving a value 0. So that's why we simply threshold at 0.5, and we find the values, the values where, I mean, the points for which the value was greater than 0.5, they are assigned the class 0. The points for which the value was less than 0.5 are assigned the class 0, and the points for which this summation average value was greater than 0.5, they are assigned the class 1. And if we run that, you can see that I mean, this is the ground truth of the level data, and this one point is sort of um, misclassified because I chose 1 and 7. They are quite similar, so to say. I don't know if, let's say, if we choose 1 and 3. I hope now the classification will be okay. No, there is still one unclassified, but you got the point, right? So here, yeah, here we have all the classifications are okay. So like we selected a class of digit 2 and a class of digit 3, and we changed these classes to 0 and 1 here, and then we loaded this x test and y test. We computed the distances of x test with every uh, training sample. We found the nearest k neighbors and cut them at k, and then we took summation and thresholded at zero point 0.5 to find out the class. So that's all it was for this tutorial. And if you guys have any questions, you guys can maybe, I don't know, ask in Moodle, or once we are done with this tutorial, maybe you guys can ask afterwards. Because there is one last thing that is left, and that is this assignment. So the assignment has already been uploaded. You guys can also have a look at that in detail. But I just wanted to go through that briefly, so that I mean, you know what's happening here. So the first, uh, I mean, this is, it already says, related to curse of dimensionality and statistical decision making. So this part is has some things similar with what we just did in today's tutorial, and this curse of dimensionality. Uh, this is actually a rather simple assignment, so to say. So the first task in the assignment says that we have a set of points CD, which is defined by all the points in a real space RP, where infinity norm is less than d over 2. You guys should know that infinity norm means that the maximum value of the x is less than d by 2. Okay, infinity norm refers to the maximum value. So this denotes a p-dimensional hypercube of edge length, because all the x's, all the variables x where the lengths are between plus 3.2 d by 2 and minus d by 2. If we expand this in, let's say, 3 dimensions, we will get a cube that is centered in around origin, and the lengths are d, which are, of course, like, which go d by 2 in one direction and d by 2 in the opposite direction, like plus x-axis and minus x-axis, so to say. So once we have that value, I mean, this is a sort of a definition of the set that we have given, and then assuming the set to be uniformly distributed in C1. C1 means d is equal to 0.1. So if C1, if a set is if x is uniformly distributed in C1, we want to find out a dependence between d and p, such that probability that this x, which was uniformly distributed, is in C1, the probability that this x is a member of CD is equal to Q. Okay, this is something that we need to derive. Then the second task, this actually does something related. It is related a bit to this complementarity, as we saw, like probability. Let's say if x is less than 2, or probability 1, or 1 minus probability of x is greater than 2, things like that. So this should also be easy for you. So we have a variable, and a certain probability is known for one of the dimensions, and then after that we know, since f x is independent, and all the components are this is like IID components, right? They are all independent and has standard normal distribution. So we, after that, we need to find out uh, this probability. So this probability actually can be, we need not mathematically do that, we can simply do that by sort of traversing from this point to this point, just like we saw here in the proof that samples lie in the tails. And then we need to do that from different p values. This is actually a task that will sort of make you more clear programmatically that samples tend to lie in the tails. So here we have like 100 uniformly distributed vectors, and we compute the angles, like we compute the minimum angle of every vector to all the vectors, right? And the angle, the formula for angles is also given. We do that for different dimensions, and we plot the result, and you will see a certain trend how the minimum angle changes when the samples, when the dimensions increase. And then there is an interpretation that we have already talked quite a lot about, so you need to have a look at that. And I would say it will also be helpful if you also maybe plot the maximum angle. I mean, if you are doing minimum, it will be just one line to see maximum. It's up to you guys. Maybe it will help in your interpretation. Just a hint. Yeah, and then there is a question: what happens if the sample size increases? So there is a question: are we assuming IID for the first part as well? Note the p-dimensional hypercube assume X to be uniformly distributed. So I don't know if we need any IID assumption here, because I think yeah, I mean there is no need of going in that direction here. We don't need any IID here, if that's what you wanted to say. NVM, I don't, yeah, okay, cool. So the next part is statistical decision making. This is, in fact, if you note, our tutorial today was also related to that, statistical decision making. So this part, again, just some jugglery. Again, we have this small probability distribution, and just some things like some sort of theoretical questions. What happens if, like, what are the, is this a joint distribution function? Is this, if this is a valid function? And let's find out the marginal. Just let's find out the joints and things, like some simple, like some simple one or two liner questions here. The last part is to show that the covariance matrix for any random variable is a symmetric positive semi-definite. So to show that, you simply need to show these two things. So C is equal to CT, and X transpose CX greater than or equal to 0 for any C and for any X. Here, uh, like this is missing, that for X not equal to 0, we should say. But anyways, I guess we have said here greater than or equal. So we are talking about semi-definite, so we need not mention that, I guess. Yeah. So this is a proof that you will need to do. So for that, if you start from this formula that we have for covariance, and then you can see how this matrix of covariance, what form the matrix of the covariance takes. Maybe that will help you here. And then if you even sort of practically try to multiply this matrix with like with X transpose CX in this form, maybe you can already find the analytical solution. I mean, you need, it's up to you whether you guys make a high level proof or uh, whatever way you go. So that's all for today, and I will upload this Jupyter notebook also, and this assignment has already been uploaded. And there is a question: is there any difference between the sampling range -1 1 and -1? uh, yeah, there is. I mean, there is of course a difference, but I don't know if you are you I don't know which point you're referring to. Task 2, task 2. task 2 and like this first bullet point or what? Okay. Yeah. So sample. I mean, if we talk, of course, like there is a difference between this scare bracket and parenthesis. That in case of parentheses, we don't explicitly include one, so to say. But here we are talking about uniform distributions, and in uniform distributions also in uh, continuous case, so to say. So it doesn't matter that much, this is one point, this one or whatever one point does not matter that much. And especially when it is in the on the boundary, so to say. So another question is one submission per group. Yeah, one submission per group. One submission per group should be enough. But I will actually, please remind me of that once again. I will see how we have like designed that in Moodle. And but I guess one submission per group should be enough. No one, we don't need like 8 submissions for 8 group members, so to say. In task 2D means that the vector is two-dimensional, right? Yeah. So it's like, it's like when we say, for instance, like when we say R2, this means two-dimensional, right? In R6, six-dimensional. So it's like, and similarly, we also sometimes say 0, 1 to power of 2. This means this is like this was the case that we saw today in our tutorial. Like we had x1 and x2, and they were like 0, 0, 0, 1, 1, 0, 0, 1, 1, 1. So we can say that okay, they are like that. So they are distributed in 0 and 1 to the power 2. And is P assumed to be finite? I don't know which P you're referring to. Maybe you can task one, P dimensional. Uh, yeah. Oh, yeah. This is you guys are overcomplicating the things. We need this is like simple. We because as you see we haven't asked about whether like what happens if in the boundary cases if P approaches infinity or anything. So we simply need to find out the solution in terms of um, D and P. So if there is any other questions, please would you please explain the box? Yeah, this has already been asked by another colleague of yours. This means that we have the random vectors that are two-dimensional and every dimension is distributed 0 and 1. Okay, so we start with the two-dimensional random vectors because it will be easy for you to plot and to, so to say, like to see what happens. Like you see, if we have a random vector in 2D, this is just a point in xy axis, right? So it will be easy for you to plot and easy for, let's say, if you have I don't know, 1,000 random vectors in this like which are uniformly distributed between 0 and -1 and 1 in x-axis and -1 and 1 in y-axis also. So when you plot them, they will be like a scattered version of a noisy version between -1 and 1. This is what I'm already expecting. So this will be easy for you to view and analyze. But you see, in afterwards we have a task that we afterwards we keep on increasing d from 1 to 1,000. So we want to see the effect when what happens if d increases, and like we actually when we actually face this dimensionality problem. Like for d is equal to, of course, we are all good to go. Yes, two dimensions and each element in -1 to 1. Yeah. So I guess um, that's all for the questions. If there are no further questions, then we can say goodbye for today. And by the way, please note the deadline also. Okay, so the deadline is 6th December. Okay, so we're not sure because of the shortage of time. We might announce the second assignment maybe even before the deadline, but we'll see. Maybe before, maybe afterwards. But please note the deadline. Okay, these deadlines are usually not flexible. I mean, we don't allow of submission afterwards. Yeah, we will be uploading this recording also. And how many assignments will be? Yeah, there will be 3 assignments. So okay, guys. So I'm going to stop the recording. I guess that's enough for today.